With this video, we will begin with a new unit, work, energy and power. For this unit, you must have this background knowledge, resolution of vectors and the scalar or dot product of vectors. If you don't know it, you must learn this first, or at least if you already know it, still it is advisable to revisit these two parts. Now in physics, work is said to be done if the point of application of a force is displaced in the direction of the force. Examples of the work are pushing a table, that is, we apply a force and the table is displaced through certain distance in the direction of force. A horse pulling a cart does work on the cart. A man climbing up an incline does work against the force of gravity. Now, for definition of work, let's find out the work done by a constant force first. Here we have two subcases. Case A, where F and S are along same direction, that is, F is parallel to S. The situation is shown here. We have an object on a surface. We apply a force F which displaces this object from A to B through a distance S in the direction of the force. In this case, the work is measured as the product of magnitude of the force and the magnitude of the displacement, which is also the distance. So work in this case is product of force and distance. Now we have another case. We have to displace the same object from A to B, but we apply a force in a different direction at an angle theta with the direction of the displacement. In such a case, the work is product of component of force in direction of displacement and magnitude of the displacement. That is, for this force F and displacement S, we take the component OQ of the force in the direction of the force. This component from the diagram is F cos theta. So work is measured as product of F cos theta and distance, that is Fs cos theta, or in terms of the scalar product we can write the work as F vector dot S vector. That is, the work is scalar product of force vector and the displacement vector. Remember, work is a scalar quantity, that is, it does not have any specified direction. Having studied the definition of work, we can now study the dimensional formula and SI unit of work. We know work is product of force and displacement. Dimensionally, force is mass m multiplied by acceleration Lt minus 2. For distance, we write L. So the dimensional formula for work is L square T minus 2. The SI unit of work is joule. The symbol is capital J and is 1 Newton for force multiplied by 1 meter. 1 joule is 1 Newton into 1 meter, or from the dimensional formula it is kilogram meter square second minus 2. We can have, say, work is positive or negative. Now let's elaborate these terms. The work is positive if the force has a component in the direction of displacement, or the work is positive when angle between force and displacement vector is acute, that is less than 90 degree. These are a few examples of positive work. Here a spring is being stretched by an applied force F. You can call it stretching force. The displacement of the force is in the direction of the stretching force. Therefore theta is 0 and the work done by the stretching force is positive. For a body falling freely, the force of gravity is downward and the displacement is also downward. Therefore in this case again theta is 0 or acute, and the work done by gravity on a body falling freely is also positive. Then when we pull a lawn roller, for example a roller in a cricket field, we apply a force in this direction at an angle with the displacement. Here the angle is acute once again, that is theta is less than 90 degree, and therefore work done by the force on the roller is also positive. Now let's see when is the work done negative. Work done by a force is negative if the angle between the force vector and the displacement vector is obtuse or greater than 90 degree. Or in other words we can say if the force has a component against the direction of displacement, the work done by the force is negative. For example, if you take this, a body moved up the plane. In this case the weight acts vertically downward and the displacement is up the plane. So there is a component of force mg sin theta down the plane which is against the displacement. The angle between the force of gravity and the displacement is greater than 90 degree or it is obtuse. Therefore work done by gravity is negative in this case. Another example, you have a body being slighted towards right. This is the direction of displacement and it is placed on a rough plane. So the motion of the block towards right is opposed by the frictional force acting towards left. The angle between the force vector and the displacement vector is obtuse or 180 degree. Therefore work done by the force of friction is negative. Another example we can take, here we have a body being moved upward against the force of gravity. The force of gravity acts downward and the body is displaced upward. Now here the angle between the displacement vector and the gravity, force of gravity is 180. Therefore work done by gravity is negative. However, one thing to be noted, we are moving the body upwards with the help of an applied force. The work done by the applied force will be positive because the force applied and the displacement both are upwards. Now let's see a few situations. Think it over. What is the sign of work done by the applied force in this example 3? And if you see this example, here we have a lawn roller being pushed by the force F, and this is the direction of displacement. You have to study the situation carefully and give the sign of the work done by the force F as it pushes the roller. In certain cases, the work done by a force may also be 0. For example, if force is perpendicular to displacement, or if force is not equal to 0 but displacement is 0, in both these cases the work is 0. Now let's take this example first. A man pushing a wall. You can see this man is pushing a wall, but the displacement happens to be 0. The force is non-zero, it's the force applied by the man, but he is not able to displace the wall, therefore the work done in this case will be 0. Or you can take this example where a pulley carrying a load and moving on a horizontal surface. The force applied to support the load is vertically upward and the displacement is along the horizontal. Therefore, the angle between the force vector and the displacement vector is 90 degree, and likewise the work done Fs cos 90 will be 0. Another example of 0 work is the work done by centripetal force on a body in circular motion. Here we have a body in long circular motion. The centripetal force Fx towards the center along radius, whereas the body moves along tangent. The velocity is along tangent, therefore displacement is along the tangent. Again, we will have the same expression, W is equal to Fs cos 90 equal to 0. We can also calculate work in terms of rectangular components. If F is Fx I cap plus Fy j cap plus Fz k cap and the displacement vector is x I cap plus y j cap plus z k cap, then the work will be F dot s, the scalar product of force vector and displacement vector, and will be given by x Fx plus y Fy plus z into Fz. Here we also need to mention the gravitational unit of work, which is kg meter or sometimes called kg weight meter, equal to 1 kg weight into 1 meter or 9.8 Newton. Kg weight means mg 1 into 9.8 Newton into 1 meter equal to 9.8 joule. The work done by variable force will be discussed in work energy and power part 2.